Hello everyone, I'm Lucy, and for our final project for this class, Yorai and I worked on pose estimation for robotic object exchange. So for this project, we were interested in facilitating object exchange between two actors in a scene, whether it be human to robot or robot to robot. With applications in areas such as hospitals, homes, and factories, this task is definitely useful in many different scenarios. So this task is multifaceted and can be broken down to two main subtasks that also need to be completed for the object to be passed. First, the pose of the object must be recovered, and next, a robot must travel to an orientation that would facilitate grasping the object in its current position. If we look at pose estimation more specifically, color-based approaches have shown success in obtaining knowledge regarding the pose of objects. However, they suffer from inconsistencies arising from changes in illumination or introduction of occlusions. Thus, in our case, where the perception system is required to operate in dynamic human space, we decided to rely on geometric information and proposed veil. Veil fits a discrete curve to the leading face of an object within a depth image. Depth images allow us to remain robust to lighting changes in comparison to a color-based approach. The two subtasks of pose estimation and actuation will be explained in more detail throughout this presentation. This slide contains a demo of what we were able to accomplish for this project. So if we look at the robot arm on the left, that one already grips the brick and is being programmed to move. The robot arm on the right is actually tracking the brick each time it moves, and when the brick stops moving, or like when the brick has gone through its program sequence, the robot arm on the right reaches out and grips the brick.
Thank you for the introduction, Lucy. My name is Yorai, and I would like to talk a little bit about pose estimation. In this project, we've been trying to estimate the 3D pose of an object in space in two ways. The first one is a visual method, and the second one is a method that uses depth information, and we call it veil. The visual method is truly pretty simple, and it makes a lot of assumptions. If you would like to know a little more, please read our paper. However, from a high level, it expects an object from a certain color, with a certain shape and a certain size, and then it fits a template to the image using the iterative closest point algorithm. Now, once those vertices are found, those are projected back to 3D space using their depth, and the pose is extracted. Now, in Veil, we're trying to do a similar thing. However, we're focusing on the front-facing face of the object, which means that as an object is crossing from the left side of the curve to the right side, the curve is fitted to that front-facing edge. Those vertices in that edge are found, and then those are projected back to 3D space and the pose is extracted again.
For the actuation subtask, we designed a function to move the robot arm in the simulation. The inputs to this function include the rigid transform object representing the desired pose, which we got from the first subtask of estimation, as well as the initial robot arm joint angles, and finally the bounds for both rotation and position constraints. The function sets an orientation constraint and a position constraint based on the given end-state pose and given bounds, and then the function solves for the desired joint angles using built-in functions in the Pydrake inverse kinematics module.
So, like we said earlier, we have evaluated Veil by comparing it to the other visual approach. And we have quantified error by looking at the difference in the poses that the visual approach and Veil have computed. Now, on the left side, we look at the perfect case, the case where all the measurements are noiseless, and we see that the error rates are pretty low. However, on the right, as we are inducing more and more noise, then we see that performance degrades, which is expected. But how does this thing actually look in practice? So, when we have no noise, we see that the arm on the right adapts properly to the movements of the objects on the left. However, when we add some noise, we can see on the top right that sometimes, when the noise is added, the curve is actually distorted. And what does that mean? It means that not only the poses would be computed wrong, but also that the arm might actually miss the object, which is not very good. However, in the real world, we assume that we're going to be in some situation that is a middle ground between those two cases.
In summary, we have presented a system for robotic handoffs involving Veil, an online method that executes pose estimation using depth images. This optimization model recovers pose information from the leading face of an object and it produced better results than the other traditional color-based perception approach. For the second subtask of actuation, we used the Pydrake inverse kinematics library to compute the joint angles of the robot arm given a desired pose. On this slide, you can see 4 examples in which we can further expand our project in the future. Thank you all for listening to this presentation, and I hope you enjoyed it.